Trish, the trig function is very cooperative in this example. In an earlier part, we found out where the trig function was increasing or decreasing. Here we're going to find out where the trig function is concave up or concave down. In order to do that, the first thing we need to do is figure out the second derivative. In the first part, we found the first derivative is 1 plus 2 cosine of x. Therefore, our second derivative is going to be negative 2 sine of x. It's going to make it pretty easy to find critical points here. We need critical points wherever f double prime is equal to 0 or f double prime does not exist. If we remember our unit circle, we need our y coordinates to be equal to 0. That's where negative 2 sine of x will be equal to 0. That will occur at x is equal to 0, x is equal to pi, and x is equal to 2 pi. From there, we can come up with a pretty easy sign test and conclusions. Remember that 0 and 2 pi are parts of our interval anyway, so we would have included them, but we will certainly consider them when we're doing our test. Here we don't even need to really consider points in between. If you'll remember, our second derivative was negative 2 sine of x, which means that our second derivative will be negative in between 0 and pi. Whenever our y coordinate originally was positive, this negative will make it into negative 2 sine of x. In between pi and 2 pi, our second derivative is positive for the same reason. Normally our sine function is negative in this region. The negative 2 will make it into a positive second derivative. So our sine function will look a little something like this. Typical waves. Concave up on the interval pi to 2 pi because f double prime is bigger than 0. Concave down on the intervals 0 to pi because the second derivative is less than 0. Pretty simple example for our trig function.